We will turn our attention to basic rules of differentiation. Even though the definition of a derivative relies on a limit, it is not the most efficient way to expand our vocabulary on functions. Instead, we're going to use algebra. Okay, we're going to use our algebra skills that hopefully you've mastered from your algebra experience to go ahead and expand our knowledge on functions. So we're going to dive into a lot of basic rules for differentiation, and that way you'll learn how to compute and be able to work with more functions just like you did in algebra class. Speaking of algebra, you might want to recall the binomial expansion theorem. That is quite useful. It's from a pre-calculus experience where it requires summation notation and the definition of a factorial. Our objectives today is actually see the proof of the power rule of differentiation. I shouldn't say see the entire proof. It's really just a partial proof just to convince you that your algebra was extremely useful in figuring out how to compute derivatives in a calculus course. We're going to gain a definition for the number e. And using this definition, we'll find out what the derivative of e to the x really is. You also need to learn both Leibniz notation and prime notation. Leibniz notation is a superior notation because it does indicate more labels and it often helps you tell a story, especially when you're working with applications regarding life sciences or the physical sciences. Make sure you're able to rewrite and implement the basic rules of differentiation. Let's begin with Leibniz notation. You've seen it probably once before, but it looks like a fraction, but it's really not. This is actually a verb and a noun at the same time. We could read this as the derivative of f with respect to x. This is just saying the derivative of f of x with respect to x. And then the last Leibniz notation here says the derivative of y with respect to x. Even though it looks like a fraction, it's really not, but you do want to make note that it does indicate your two very important variables. The independent variable is there, and your dependent variable is upstairs. Okay, your dependent variable is right there. So your independent is symbolized, and then your dependent variable is also symbolized with Leibniz notation. That is why this is often a more important notation. It is just far more superior, and it will help you tell stories or indicate certain labels regarding the physical sciences and the life sciences. If you need to recall the binomial expansion theorem, it's right there. Okay, this is going to be used to convince you that this derivative rule is actually true. Okay, this is a derivative on a very simple polynomial. However, n does not have to be a positive integer. It actually could be any real number. The proof below is just a partial proof. It's just a proof for the case of the positive integers n. You could walk through it and just follow the algebra and convince yourself that, hey, this rule does really work. Not only will it work for positive integers n, it will also work for any real number. Okay, that's going to be very, very powerful. That means you could actually use decimal exponents, you could use fractional exponents, and then actually apply this rule. Notice the proof just involves the difference quotient and using algebra to simplify each step along the way. You're just simplifying the expression, and then until you get to a determinate form. When you get to a determinate form, you could go ahead and take the limit as h approaches 0. As h approaches 0, you end up getting that expression, which is a function of x. And so the derivative of x to the n is simply that. It is extremely useful. I mean, look how useful it is. We could just go ahead and simplify this expression. Example 1, go ahead and simplify this expression. You just put the 99 to the front. Oops. And this would be 99x to the 98th power. Okay, so the Leibniz notation encourages you to perform an action. Take the derivative of x squared with respect to x. That's how you read that. Derivative of x squared with respect to x. And just like that, you are done. Because of this rule here, there's a certain pattern that you'll perform. It's a computing pattern. It's not too difficult. It's the first basic rule of differentiation that you need to master. Here is a Desmos tool to give you some insight on why this next definition of E is so important. So feel free to pause the video and take some time to do this Desmos exercise. And like I said, it gives you insight to this definition here. It is very hard to understand why certain definitions in mathematics are created until you see it graphically, or you see it in context, or you see it in another example. Speaking of another example, why don't we continue? Why is this definition created? This is a definition for the number E. So why don't we investigate the difference quotient here? Okay, why don't we investigate this difference quotient for f of x equals the exponential function e to the x power? Let's start with this expression here. Literally the definition of a derivative function, and we simply substitute. We simplify the next expression. Now you do need to master your rules of exponents. You master the rules of exponents, you have a chance of understanding calculus. Notice the numerator has a common factor of e to the x. And so I'm going to factor out an e to the x there and see what is left. And that should look very familiar. It's actually the definition of e from above. There it is. Now h is your variable. That means e to the x here acts like a constant. So if it acts like a constant, we could actually write the following. E to the x is multiplied to the limit as h approaches 0 of this quotient here, which is part of the definition of e. We know that value is 1, so e to the x times 1 is what you have left. I'm going to put a period there. I'm going to make a conclusion, a very important conclusion. Therefore, the derivative of f of x is in fact equal to the x, e to the x. More importantly, you gain this derivative rule, or this basic rule of differentiation. The derivative of e to the x with respect to x is now equal to the original function. And that is pretty cool. That is really, really awesome. That's not a factorial symbol. That's just me being really, really excited about this basic rule of differentiation. I'm actually going to go ahead and circle the entire proof. Because once again, the previous sentences is actually the algebra that you need to really understand all the calculus ideas. Suggestions for more basic rules of differentiation. I recommend that you memorize them. You don't necessarily have to memorize these in order, but it's kind of nice to know that, okay, these first two were introduced, so we could label them 1 and 2. But in reality, you need to know all of these at the same time. I shouldn't say at the same time. You can only perform one rule or one tool at a time, but you never know which one you're going to do. So you might as well just rewrite these and memorize them as much as you can or as soon as possible. So if you need help memorizing these things, you could make flashcards. I mean, you could put this on the front of a flashcard, and then you could put this on the back of a flashcard. Remember, the double bar symbol means to have the same value as, okay? That double bar symbol means to have the same value as. So here's some practice after you've memorized those rules. You just need to execute your mastery of algebra and you're on your way. So this is a good time for the next 5 or 6 examples. You might want to pause the video and go ahead and tackle these problems on your own. And if you seem to be stuck, then go ahead and play the video, and you could use the video to check your answers or to check your writing or to check your composition to see if you are on the right track. Remember, any mistake you make, you need to correct it as soon as possible so that you don't make that mistake again. First function, a very popular function, it's a reciprocal function. So in algebra, you can look at it in a couple different ways. You can look at it in terms of exponents, and there it is. We're going to go ahead and execute Leibniz notation first. So we're going to take the derivative of f of x with respect to x, which is going to be this. And then we switch it back to positive exponents like you did in algebra. We're going to conclude, though, in the other notation, which is a function of x. We're going to conclude with prime notation. And we'll go ahead and indicate the domain. It's always good to analyze the domain of the original function and the domain of the derivative function as well. So look at this domain. Notice that it does match with the derivative. You'll realize that it doesn't always perfectly match, but you should always pay attention to the domain, just like you did in an algebra course. Here, we're going to take the fourth root of a radical. That means w here must be greater than or equal to 0. So we know that the domain of G, here's another way of writing domain. You'll see me write this from time to time. So the domain of G is like that in interval notation. However, once again, using your mastery of algebra, you can see that G of W can be rewritten as such. And now we'll go ahead and execute Leibniz notation, derivative G with respect to W. The constant stays in front, and now we'll do, the power rule. Now we're ready to convert this back to prime notation. And there it is. Notice the domain has changed a little bit. Domain of G prime, or the domain of the derivative function here, is not including 0 because you can't have 0 in the denominator. So very close to the original domain, but not the same. A few more examples here. Start with Leibniz notation, and we'll just simply simplify the expression. Make sure you conclude with function notation. It's very important that you learn both notations. Both notations are necessary in the study. We'll later study something called implicit differentiation, along with the chain rule, and along with related rates of change. And that does require Leibniz notation. It requires the derivative of f with respect to t. The prime notation often is hiding a lot of missing information, and the Leibniz notation is often exposing that information. So the Leibniz notation is actually more important. This next example, once again, your mastery of algebra is very, very useful. We're going to do a quick distribution just so that we could look at this a little bit differently. So this is just a reminder of what quick distribution looks like. This is a shortcut on the distributive property. You don't have to use this shortcut. I mean, you could just simply distribute as long as you are understanding that you have to perform some kind of distributive property here. So we're going to rewrite y of x. And now we're ready to take the derivative of y with respect to x. Sometimes I draw a wavy line here just to get you to realize that we changed procedures. We're going to go ahead and simplify the next expression. $18 times 3 is 54. And so notice I am simplifying the expression, and we're following the etiquettes just like you did in algebra. We're trying to write a polynomial in descending order. Let's put a period there because I'm going to conclude with function notation anyway. So it's a fourth degree polynomial. The cool thing about polynomials is if you start with a polynomial, the derivative is also a polynomial. And we already know the domain for any polynomial is all real numbers, or the interval that consists of the entire number line. So notice the domain of y up here is the same as the domain of the derivative function. Let me use parentheses here. A few more examples here. Look how fast that one was. The derivative of y with respect is simply e times e to the x. And notice the domain for y prime is actually all real numbers. The original function was also all real numbers. This one here, you might want to use a different algebra idea. You need to know this simplification. This is a formula. Hopefully you have mastered it as knowledge. If not, you got to write it down and try to remember it. Just like you are trying to remember all the basic rules of differentiation, you do this with practice and persistence. I'm going to rewrite h of x to make it look a little bit nicer. And once you have it in this form, taking the derivative of h with respect to x isn't so difficult. I could draw the wavy line here again to let you realize I've changed procedures. Therefore, we'll write the function notation. The derivative function is a function of x, and it simply looks like this.